Ladies and gentlemen, welcome to the second talk of this session. The speakers is Tobias Ekholm from Uppsala University and Institute of Metallefleur from Sweden. The speaker is known for his work in topology, symplectic geometry, and mathematical physics. Today he will talk about the skein value mirror of topological vertex. Join me to welcome him.
Thank you. So I would like to start by thanking the organizers for getting this great event together, and also for the kind invitation and for the possibility to speak here. So my topic today will be it's going to be about the topological vertex, and this talk will report on some joint work with Pietro Longhi and Vivek Shende. And there is an archive identifier there. And if you want to find, I'm going to say many things and not give references to everything in the talk, but all references should be in that paper. So the plan here is that I will talk about first, in general, skein-valued curve count. So I will be a little bit quick on that. But the idea there is that if you want to count open holomorphic curves, or if you want to count holomorphic curves with boundaries, and you want to have an invariant count, everything will be in dimension 3 and so on, then you have to take into account the knot theory of the boundaries of these curves. So somehow this Homfley polynomial and so on will arise naturally. Okay, so that's the main observation to get invariant count, but this talk in some sense is about an application of that technology and that philosophy to what's known as the topological vertex. Topological vertex is a certain configuration of three Lagrangians in just complex 3 space, and on those Lagrangians form some holomorphic curves, and we'd like to count them. And typically, and it's been known for a kind of long time, this vertex was studied in physics first, but there was a lacking definition for these invariants, but still the count was done, and it can be used in closed Gamma-Witten theory and so on. So we will somehow carry out that count in this new language. And as it turns out, there is a general principle that was not used so much in this subject, that if you go to infinity, so these are non-compact Lagrangians, I'll explain all of it, and you look at infinity, then there are very simple curves to find there, and they actually know everything about the curves inside. So what in the end we will find is we'll find a new recursion for the topological vertex that somehow determines it, and also shows that somehow the count is the expected one in some way, but it also shows that this skein-valued thing is compatible with what was done before. Okay, so but I would like to just start with giving the setup and for this skein-valued curve count. So we'll start with some kind of symplectic Calabi-Yau threefold in our case, so it will be just a complex 3 space, so it's very simple. And what does it mean? It means that we have a symplectic 6 manifold, and when you have that, on there is a homotopically unique, almost complex structure, and Calabi-Yau condition says that first Chern class of that is 0. And inside this 6-dimensional manifold, we will have a Lagrangian threefold. So a Lagrangian 3-dimensional manifold. In our case, it will be simple. It will be just S1 times R2. And we have to require, in order for these curve counts and so on to make sense, that it's orientable, it's spin, and the Lagrangian condition is that the symplectic form vanishes along L. And this Maslov condition, well, if you have C1 of X 0, then there is maybe complex volume form that trivializes the tangent bundle, and the orientation bundle of L gives you a real line in this bundle. And so if you walk along a cycle in L, you can sort of see how many times you turn around, And here we require that whatever cycle you walk along, you turn 0 times around. That's Maslow's 0. So that's the ambient geometry. And now we are going to look at holomorphic curves in this setup. So that means that we look at maps from a Riemann surface with boundary that goes into X and takes boundary into L. Okay, and our curves are holomorphic if they satisfy Cauchy-Riemann equations. So we fix one of these complex structures, and we require that the differential of this curve is complex linear. Now this differential equation is elliptic. So we can compute the expected dimension of the space of solutions around, say, a given solution by Riemann-Roch formula or index theorem, and the dimension formula in general looks as follows. So we have an n-dimensional Lagrangian 2 n-dimensional ambient manifold. In our case, n is 3, and the dimension is given by this formula n minus 3 times Euler characteristic of the surface plus twice the first Chern class, which have to be a relative Chern class when you have Lagrangians. So basically look at the obstruction of extending the trivialization over this surface. And in our case, we have a kind of the two good conditions. So one is that n is equal to 3. So therefore the first term vanishes, and the other one is the Maslov 0, which tells us that this C1 relative also vanishes. So that means that if you find any holomorphic curve, you kind of expect them to be discrete set after suitable perturbation. Of course, when you find them, they're never discrete, but after perturbation, they would become some discrete zero-dimensional set. Okay, and then, so I want to first describe to you this closed Gromov-Witten theory in enlightening overview. So what's the closed Gromov-Witten theory? Well, it's the theory that counts this closed holomorphic curve. So in the case S has no boundary, just throw in the Riemann surface there, you solve the bar equation, you should have some number of points and you want to count them. So this Witten in Gromov-Witten is that you think of this as a calculation of topological string partition function, and that's some kind of path integral. I'm not going to give you any details. But in this case, the path integral localizes on holomorphic maps. So that means that the integral becomes an integral over the moduli space of holomorphic maps. And if you perturb them, so there is a little prime there in the sum, this integral would be just a sum over all the maps. And in the sum, you see that how they're counted, so that there is a W of U, so it's a weight. So each point normally, if it would be kind of normal problem, then it would be counted as +1 or -1 because of orientation. But now, since we're counting maps and there might be automorphisms, this is really an orbifold point. So there could be some denominator. So that's this WU, and then you take it to the exponential minus area weighted, and then there is the string coupling constants, as it's called, so this genus parameter that keep tracks of the genus of the curves that we count. So that's the sort of Witten in the Gromov-Witten. And now what about the Gromov? Well, the Gromov or mathematical treatment of this would be to forget about the first path integral and so on and start from this discrete sum. So we have some moduli space, which is in this case zero-dimensional. So it's very easy to deal with. And now we'd like to check that if we count up the points in this space, we get some number. And one would like this number not to depend on, say, the choice of complex structure or something like that. From the point of view of topological string, this is some kind of, you can see that in the path integrals. Path integral changes by exact form when you deform. But from the math point of view, you would like some other argument, and the argument is here. So to the left, you see some kind of parameter, which is time. So you can think of it as parameterizing choice of complex structure, or really, you need to, when you do this, it's a difficult story, but you need to perturb the right-hand side of the holomorphic curve equation, and since you count all the curves, it's very complicated. But I'm not going into detail there right now. So we have this one parameter family of data, and if nothing happens in the sense that it's a normal elliptic problem and no kind of breaking anything, then we would find a one-dimensional, as we vary t, we find a one-dimensional manifold of solutions. And that gives you a cobordism from the points on the starting at 0, where we start our problem, want to count them, to the points at 1. And of course, the number would then have to be the same. So this is somehow this invariance of Gromov-Witten theory. Now, this holomorphic curve equation is almost that good, but by Gromov compactness theorem, it's not quite the case that you can say that you continue this solution in time, but you can continue it up to what's known as bubbling. So energy can concentrate someplace, and a new, as indicated in the picture, something like that can happen. You can start with some curve, and some other curve bubbles off. But if you look at this phenomenon, then you have this shrinking neck, and maybe you change coordinates, so it's conformally a long cylinder, and you see that there are two real parameters involved. Is the length of the neck, and is somehow the rotation. In other words, if you want a very simple model of this breaking, look at the equation just in the plane in C2. So you have x times y is equal to epsilon. So this is, of course, the kind of curve we all know and love. And when you take epsilon to 0, it breaks into two lines. So this is a kind of good picture of breaking. But you see that the breaking or the nearby curves are parameterized by epsilon in the complex numbers. So going to 0 with epsilon is kind of codimension 2 phenomenon. And it basically tells you that the true situation when you try to do this perturbative, find this path t up there, is that if you find a singularity, you can actually go around it. So you can avoid this splitting if you want to connect M0 to M1. And so the picture on the left is correct. So that somehow, in oversimplified maybe version of why Gromov-Witten invariants are invariant. Okay, so famous example of such a calculation is the calculation Faber-Pandre-Panda, I guess, first in the resolved coniform. So if you have a P1 and you take O minus 1 plus O minus 1, you have a 6 manifold, and it's somehow very easy to see that it's local P1, as they call it. So this sphere sits there, and every holomorphic curve actually has to be a multi-cover of this sphere. And now you can try to count all these curves, and you can actually do it. And the count is this famous formula. So I'm calling the area of the sphere A squared for some reason that will appear later. And you see that there are a lot of contributions, and as is typical in this theory, if you put, so this exponential means that you count all disconnected curves, right? But if you put d is equal 1, you see the sphere, and that would contribute 1 over gs squared, but you actually see the denominator there, which is 1 over q minus q inverse, where q is this e to the gs half. So one might ask, where do all these curves come from? And they come from the sphere, kind of embedded sphere, with constants attached to them. So when you perturb, these constants get some life, and you should count them. So I'm not going to, of course, prove this formula, but I still want to say it because of what comes next twice. Okay, so now we would like to repeat this story, but we'd like to repeat it for open curves. And so the starting point of this story is more or less the same. You can write a path integral for topological string, and it also localizes in holomorphic maps, and it should somehow be invariant under deformation. But if we go and do the analysis that we just did for the cobordism, we find, and I write the local models here, pictures will appear on the next slide. So we find that, remember we had this model which was xy is equal to epsilon. Epsilon is complex number. Now instead we have to, because we have boundary condition, local model would be xy is equal to epsilon, where epsilon is real. Okay, so that's one local model. But over reals also, x times y is not quite the same as x squared plus y squared, which is sort of the complex number. So we have two local models. And the main difference is that epsilon here, real parameter. So that means that in the space of moduli, we have codimension 1 walls. And when you hit such a wall, the curve count would naturally change. So if we look on the left there, the little curves up here, maybe I don't know. Anyway, these little curves, they are the boundary of some kind of maybe very complicated holomorphic curve, but I'm drawing a little piece of the boundary. And as I tune my parameter, the curve is breaking. And in fact, at that point, the moduli space is ending. Right? So if I naively try to count this curve, say that this one was a disk that comes and pinches itself, then my count would not be invariant. I mean, I start with counting 1 and I end by counting 0. So that's not so great. But if you look carefully at this, you can look at the point when you have this nodal curve, you can go to the normalization of the curve. And you find another curve. So for example, if this first one was one disk that comes, it could be that it pinches and it becomes two disks, right? So it's somehow that you lift apart. So the normalization of the curve is another moduli space. So at this point, they are identified. The kind of, say, two intersecting disks looks like one pinch disk. You can draw other such whatever models you want. And here there is another moduli space that passes right through. And the difference is that moduli space, in that moduli space, the boundaries cross. Okay? So now, if we could count it up in some way so that the sum of these two guys is equal to that, if we postulate that, then we would have an invariant count. It wouldn't change under this wall crossing. And that's exactly this first skein relation. So if we say that this one minus that one is equal to that one, and there is a times z here, so that power of z keeps track of the Euler characteristic of the curve that we count. So if we postulate that, then we somehow, the count is invariant when we pass this wall. That's the first relation, and then there is this kind of elliptic one, which x squared plus y squared is equal epsilon. We see it here. On the Lagrangian, we see a circle that shrinks and goes away. And when it goes away, the curve, loses a boundary component, but at that point where the circle shrinks, the two-dimensional curves intersects the Lagrangian. Right? The normalization intersects the Lagrangian. It's a two-dimensional holomorphic curve intersecting a three-dimensional thing in a six-dimensional space. So that means that just like in the real case, the boundaries are crossing, in this case, the whole curve crosses through the Lagrangian. So again, something changes, and if we set up the same equation, we would again be safe and have an invariant count. So we are introducing now a variable a, so that's a customary variable in knot theory, and we count things with, we need to take into account the linking number between the curve and the Lagrangian. So because we are just crossing at this point, linking number changes. So we say that the difference between these two curves, they are depicted here on two sides kind of the Lagrangian, is equal to z times the unknown. Then again, we cure this wall crossing phenomenon. Okay, so this linking is a little bit tricky. Namely, if the curve was just a sphere, linking Lagrangian like this, then it's easy, right? Then we can define some linking number. But now the curves that we count, they actually have boundary in the thing where they want to link. And so, of course, you have to say something in order to regularize this. And you have to push them off in some specific way. And the way we do that is the following, that we pick some, assume that it exists some kind of four-dimensional change, maybe non-compact, with boundary on L. And we require it to end along a given vector field. We push the curve off in direction j times the normal of the given vector field v and the tangent on the boundary. So then it's safely off of this four-dimensional chain, and you can take the A power by counting with this chain. So this is a good definition, but the price that we have to pay is we need to look at the boundary as a framed link. And this third relation comes from moment. So generically, the tangent would never be parallel to this reference vector field that creates the four chain. But in one parameter families, it could become. And so we have to count the framing. Somehow, if I change the framing, I pay an A power. And it can be checked in local model that when I do that, I go from this kink to some interior intersection. So this is what happens with this four chain. Okay, but these three relations are known as the as the Homfley-Skein relations. So, in other words, what I now sort of explained was the following: that if we try to count holomorphic curves in X, boundary in L, it seemed like we had a big problem. We somehow count them, but we see that the count is not invariant. But if I impose these relations, then the count is invariant. And what it means is that I should count my curves as follows. I should take my curve. It has its weight as before. Then I take z, this variable Euler characteristic, to the minus Euler characteristic. And I take a to this linking number of the curve and Lagrange. And then last, I take the value, I take the boundary of the curve, and I consider it as an element in the skein module of L. I'll tell you what it is. It's down there. And then the count will be invariant. Okay. And the skein module of L is the following. So we take these A and Z variables, positive, negative powers, and then count over rationals. That's basically this guy. And then we take all the framed isotopic classes of nodes. So they're framed by tangent and this four-chain vector field, if you wish. And then we divide out by the three skein relations. So this is something that appeared in knot theory and it's well studied. It's called the skein module, frame skein module of L. So if we take our curve count to be valued in there and we count curves like this, then we have an invariant. Okay? And there is one more comment, and that's related to what I said about the sphere. So here, the count, we don't count really the usual curves in Gromov-Witten theory, but we count without perturbing the area zero curves. So in some sense, we don't really fully perturb out, and there is some kind of, that's not free of work. You have to prove theorems that you can actually do it, but I'm not going to discuss that with details, but it's important to remember. So if you see, for example, an embedded disk, it would be counted by 1 over z times this disk, and if you would like to relate it to some perturbative count, you have to do something like this. E to the gs so z is e to the gs minus e to the minus gs. So it's a lot of curves coming from simple curves, if you think like Gromov-Witten. Okay, so let's do a couple of examples on this skein module. So if you go to the three sphere, which is where of course everything started, so then this skein module itself is just a polynomial ring, and that's the statement that there is a Homfley polynomial which is invariant for each frame node. So somehow, yeah. So there by these moves you can undo any node until it's empty, and you get just a polynomial, and that's the Homfley polynomial. So the other case that we will need is we need the skein module of the torus. So it's torus times R, we get the three manifold. And this is a very nice module. It has a very natural basis. So there, if you skein, you draw a knot on a torus times R, and you do all these moves. Well, then you cannot, for example, change the homology class of this torus, so you cannot expect that it cannot be a polynomial ring. So one can ask for some generators and relations, and the generators are the natural ones. So if you take a pair of relatively prime integers, you can draw on the torus an embedded curve in homology class ij. So those are generators, but then we need to say something about what about generators of classes which are not relatively prime, so like 2, 2 or something like that. Well, what you do is you draw the underlying curve and insert over that curve this funny combination. So you take a connected curve first with all over crossings, you change one of them and change all of them, take the average with that coefficient. And you can ask, why do you take this coefficient? Well, you take that coefficient so that you have this very nice commutation relation. So when you have elements in the torus, you can somehow multiply them by stacking. So if you take this Pij above Pjk and take minus the other way around, then you get this nice expression. So it's a very nice basis in this way, and we will not make super much use of it, but a little bit. And here there appears this thing that will be throughout, that our z is q minus q inverse. So that's because some of these operators sometimes needs to be inverted. And it's easier to use z. Okay. Finally, we will need the place where we're really working. So that's solid torus. And solid torus has also, you need sort of an infinite basis. And here there is a particularly nice basis. Maybe I go directly to those that go positive around, so they're positive. So they're enumerated by partitions of integers. So lambda is somehow you should think of as whatever this diagram is with boxes, right? So it's partition of integers, and they have the property that they are. Maybe I'll draw these over here. So this one would be P10, and P00 is just a small unknown. And this outside algebra acts on nodes inside by just taking union. So you will have a yellow node inside. And what we're saying is that these W lambdas, they're actually eigenvectors of this operator, and they have distinct eigenvalues. So it's a very, very nice basis from this point of view. So the simplest, this is actually a calculation we will do. So the simplest example of an open Witten invariant is this toric brane in C3. So you will see many pictures of it, but here you should think of an S1 times R2 with one single holomorphic disk forming on it. And then there can be multi-covers of these disks and so on. We can ask whatever is it counted. And it's counted like, take this funny note that you saw on the previous page, divide by this Q thing, and takes an exponential. And that turns out to be equal to this expression in terms of W lambda. So maybe the details are not so important right now. We'll see it in a minute again. Okay. So this is the framework that we will use, and we will use it to study this topological vertex. So what is topological vertex? Well, I'll give you a super short overview of what it is. So it's supposed to be the topological string partition function of three particular solid tori in C3. I'll draw a picture in a second. This object has had many incarnations. In particular, it can be used to compute certain closed Witten invariants. And I just, in order to get a feeling for what it is, here is a formula. If you never saw it, it's probably hard to follow, but this is kind of explicit formula in terms of skew-shore functions. So one can write some other formula in terms of Hopfli polynomials of a Hopf-link and so on. But anyway, I want to say that it's a fairly little bit complicated but explicit formula. And those of you who know Shor functions, this looks like some very infinite power series, but you can actually simplify it by geometric series to be polynomial for each, or rational at least, for each given three partitions. So basically you think of it as a machine takes three partitions, spits out some Q series. Okay. And I want to just say just illustrate why one of the reasons it became popular. So here is a kind of toric picture of this local P1 So O minus 1 plus O minus 1 over P1. And as the picture indicates, one of these tori that I'll show you explicitly soon basically cuts this sphere in two halves. And now we have this disk that we had before, which is sort of part of this topological vertex, one this way and one that way. And there is a gluing formula that tells, write down partition function of one of them and the other one of them, and then insert a delta function on representations in between. Multiply and you get the result. So now if you know toric geometry, you can imagine much more complicated diagrams, but you can always cut it up into maybe trivalent vertices and then try to kind of reunite this thing. And what we are going to do today is we're going to find partition function of the three branes. So maybe I have the picture, sorry. Here's the picture. So this is a picture of C3, and we have three solid tori sitting there. So those are the ones, and as you see, there will be very concrete formulas for these branes. But before that, let me tell you the main result now. So we have these somehow three solid tori sitting in C3. And there is one holomorphic disk forming in all of them, and you have to understand all the holomorphic curves that they give rise to. Okay, and what we will show is that there are three operators in the skein, three operator equations, I should say, in the skein of the three tori at infinity. So this is the this is one of the equations. So you see you have a combination of unknot minus meridian minus longitude in the first torus, and the other one is unknot minus a sort of minus 1, 1 curve and another three simple curves in each one of them. And these three operators, they now operate on the curve count inside, right? So inside each one of them, we have a lot of holomorphic curves forming. They give some element in the skein, which is very big. But these operators, they actually annihilate the partition function. So here you see one equation. You see A. Remember, in the Homfly module, the Homfly skein module was a polynomial ring of A and C for some Lagrangian. Here we have three-component Lagrangian, so therefore we'll have three A variables, one for each Lagrangian. And so those A's appear here in this equation, and you can get the other equations by just cyclically permuting the indices. So it makes it easier to see where this comes from than to state the equation. So now the main theorem says that, indeed, as I said, these three operators annihilate the count of curves on the three Lagrangian tori. And moreover, there is a very natural initial condition that says that if it doesn't go around anything, then there's no holomorphic curve. So the power series for this one starts with 1. That's the initial condition. So together with that initial condition, the three operator equations determines the solution uniquely. And we verify that the solution, as expected, is given by this kind of formula for topological vertex. So that one solves this recursion after some messing with transposes of representations, but that's in order. Okay. Okay. So now let me go on and then try to explain how one could prove such a thing, and the proof is somehow not so very complicated compared to other things that was done for this vertex. So here are the three tori. So you see, we have three parameters. So we have a rho, which is somehow radius going off in this picture down here. That's this parameter. And then we have two alpha and beta parameters, which gives you a torus at infinity, basically. But important to note is here that I shift them. I have this R1, so that's this distance. So if you put rho 1 is equal 0, you see that there is a holomorphic disk in the first plane bounded by this torus. So that's somehow drawn in this picture as this line here. And similarly for the other ones, so they sit there and they have, each one of them have their holomorphic disk, which is the easiest disk you ever saw. It's a unit disk in the coordinate planes. So these three disks intersect, and then what we're trying to understand is what kind of holomorphic curves do we get when we look at all the covers and all the constants and everything attached to this. And that's sort of what we answer. Okay, so what we are going to use is that we are going to go off to infinity. So in these formulas, we are going to look at the rho 1, 2, 3 limit of this thing. So we take rho extremely large and see what's the asymptotic. And the asymptotic is this torus. So this little R1 and R2, it doesn't matter. So we asymptote to this Legendrian torus in standard contact S5. So at infinity in C3 sits the S5. On that S5, we have, from the symplectic structure on C3, a contact structure where the Rabe flow is just, you stand at the point, you take the outward normal, multiply by complex structure, and you go around. So it's a periodic Rabe flow, which gives us just a Hopf vibration of S5 over CP2. Okay. And there sits these tori. And there is one thing in the treatment of this vertex that was somehow not well explained before. So there's this theta j here. It's typically taken to be the same theta j equals 0 for all the three branes. But that's somehow, so they schematically, if you do that, they kind of asymptote to the same lambda up here. And then curve counts not really well defined. You need to, so this is somehow too close to something like that or to this. So you cannot say whichever curve count it is. So here we take the most symmetric possible location. So we take one not shifted and the other one shifted by 1/3 of a turn for each one of them. And then we have a C3 symmetry, so at infinity, lambda 1 to 2 to 3 and 3 back to 1. No, that's the wrong direction. Okay, so in this subject, in symplectic field theory and in knot contact homology and many other things that happened over the years, it's a good idea to look at curves forming at infinity. And these curves, they have asymptotics to Rabe chords or Rabe orbits, so they kind of not closed curves, but they have a boundary at these Rabe orbits. And so at this point, we would like to understand them. And the torus that we just drew, when you project it by Hopf vibration down to CP2, you find the Clifford torus. So if you take coordinates C2 times 1 on CP2 can project it, then it's just the product of the two circles. 2 unit circles. So we find some holomorphic curves there, but just the disks that bounded by this torus. And in order to find the holomorphic curve on the actual torus, they are invariant. You just have to pick meromorphic sections over these disks that begins and ends on Rabe chords. So it's somehow pretty easy to do that in this case. So we'll do that very, very shortly. So let's first look at what kind of Rabe chords there are. There are infinitely many because we have this periodic Rabe flow, but the shortest one are very easy to find. So here is the Hopf fiber. It's a picture of the Hopf fiber over one point at the Clifford torus, or any point at the Clifford torus. And so our Legendrian torus, say lambda 1, correspond to the 3 red dots. So they're kind of 2 pi over 3 apart along the Hopf fiber. Next torus, the 2, is obtained by the first one by rotating it, whatever it is, 2 pi over 9. And the next one is rotated 4 pi over 9. So now we can look at what kind of Rabe chords we have there. And we have, we look at the Rabe chords of action or length less than 2 pi over 3. So for 2 pi over 3, we can go from 1 to 1, or 2 to 2, or 3 to 3. And if you perturb it, Rave cores would be isolated, but here we have a family, so it's a bot situation, but the family is parameterized by, say, starting point. So we have a lambda 1 family of such chords for lambda 1, lambda 2 for lambda 2, lambda 3 for lambda 3. And then you have slightly shorter chords from 1 to 3, or from 2 to 1, or 3 to 2. So they're actually 4 pi over 9, and I call them B. They should be, so this should also be B. I'm sorry about that. And then we have the shortest ones, which are 2 pi over 9 chords. And they go from 1 to 2, 2 to 3, and 3 to 1. So in order to do what I'm going to do, I would like to perturb out of this Moore situation, bot situation. So I'm not going to say very much about it, but we're only going to use the minimum chord. So there will be one minimum for each family. And we can now somehow find all these disks that I was talking about. So I'll explain with details soon, but let me first state the result. So this first one is maybe a little bit tricky to find, but that was the disk that sits in this plane of the Clifford torus with a certain section. So I'll write the explicit formula on the next slide. But then other holomorphic curves that could be here, they have, say, positive puncture at this C Rave chord at the 2 pi over 3 length, and some other negative Rave chords. So the projected area of such a thing would have to be 0, which means that the curve actually lives in the fiber of the Hopf vibration. So we have some kind of infinitely easy problem from complex analysis to solve. And what we find is we find two triangles in the fiber. We're kind of going, let's see if I have, no? Here is some picture. So this is a typical such. We draw one Hopf fiber. Here is the disk. So it's at the infinity, it's going this way, going down, making kind of jump to this one, branch point, jump to that one. So there is such a triangle, and there is some other smaller triangles as well. So we have these ones are big. So from C to B to A, and then we can also go B, A, A. So that's a little bit smaller triangle. So we also have in the fiber quadrangles with 3 negative punctures. Of course, we don't have to jump only once, but we can jump once and jump another one. And in this picture, you see that the moduli space has some kind of boundary where one of the triangles sinks into this point and the other one leaves. And the other, that's called SFT or Hofer compactness. But this is too simple to be called that, but okay, in the general case, that's what it is. So these are our moduli spaces, and here is some kind of formulas for these for the 3 disks. So you see, it's pretty simple. This is the Hopf vibration thing where we just have a variable z, but then we normalize the thing to have a pole on the boundary wherever we want. But that's at the minimum we take it. So anyway, the main thing here is that if I use these explicit formulas, I can also write explicit formulas for the boundaries of these curves, the 3 curves which you see there. And if I instead move to pictures, what they look like is the following. So these were the triangles in the fiber, and if I fix one point, fix one Rave chord, so I put it, this is supposed to be my torus at infinity, so I identify upper and lower edges and right and left. And then I have these 2 Rave chord endpoints, and I have 3 curves that look like those curves. Those are the boundaries of my 3 disks. Okay, and then I'm claiming that this data, together with this kind of skein valued counting, actually will determine for us the partition function. So let me tell you how this goes. So the main idea is the following. So let's look now at this moduli space with positive puncture at C11, okay? So what is this moduli space? So when we do the skein valued curve count, we cannot think of this moduli space at infinity alone. But we have to look at all the full one-dimensional moduli space means that this joint union of the thing that's one-dimensional here and that contains all the closed curves inside. Okay. So this is some one-dimensional disk that we saw. And it can start moving inwards into the solid torus, and it moves. And by this kind of Gromov compactness, as it hits this Z, you know, it could hit and join and so on. But we are considering curves in the skein. So that means that every time you hit something inside, you just go on, right? You do the skeining, you go on, you didn't change the count. So it means that if you take the totality of the moduli space of all the curves that has positive puncture at this C11, then its boundary in the skein must be 0. So what is the boundary? Well, the boundary are these three disks that move to infinity, just times, and times means acting like in this picture. Right? There's a disk out at infinity. Inside there's the whole, all the collection of all the closed curves. Right? Plus the other way it goes to infinity, plus the third way, plus these two triangles that we had, which are in some sense bad terms, and I'll tell you how to get rid of them. But here you see the triangles at infinity, whatever curve that could fall down and attach to them at this Reb course, as this SFT compactness. And again, you see somehow Z sitting intertwined in some weird way there. But so if these guys were not there, if I pretend that these two were not there, then I would find an operator equation. My operator would be these three disks. Those P, so it would be, in this case, maybe this one as well. So I would have something like, that's what happens if I have just, then I find such an equation. And that might be used to solve for Z in lucky situations. So our problem for the vertex is that we have these kind of strange terms. So there, I number them 1 and 2 because I copied them from the next slide. So you'll see in a second. So the whole scheme here is to try to get rid of such terms. So maybe this guy can be cancelled. You know, if I find some other disk that looks like this one, maybe I can cancel it. And indeed, this is the situation for C11. And of course, I have similar situation for C22 and C33 because they're the same. This is the C3 symmetry. So I have three equations. So these are my curves on each torus. Sorry, on each torus I have these three main disks. So on L1, on L2, and L3. And I have these triangles that was also drawn also on 3 torus. And I know that if I act on the partition function and with these weird things attached, then the result of each one of them is 0. So if I could find some kind of linear combination of the three so that these guys cancel, then I would be in business. Okay? Because then I would find some sum of three things which annihilate the partition function. And that was in fact exactly, if we look all the way back, so that's what we're going to do, and I explain how it works. But where's my A? Here's my A. So you see that this is exactly the form of this one. It's this one plus that one with some A powers that one has to determine. But basically it looks like three such equations, you sum them up, and you annihilate this Z. And so that's what's going to come out of this analysis. Okay. So, how to understand this? So there is somehow this. I worked on this for actually for a long time, and one of the main things that was confusing to me was this sign. So this sign is really crucial. So let's see. So we would like. So if there is a minus sign, we have to look at this thing. So first of all, if we look at this curve, it has one boundary component on 1 and the other on 2. And it has these positive puncture B21A, negative punctures B21, A12. And there is a friend of it, which is here. It has one boundary on 1 and one on 2, and the same negative punctures. So these kind of monstrous curves that attach to this one is the same one that attaches here. So if we could match these two terms, then we would be in business. And, well, basically this curve here tells us how we would have to choose. This gray curve is something up to us to choose. And we choose it so that this one matches with this one. And then these two has a chance of canceling. But you see that there is now kind of some, and this one should cancel with this one. So there is some kind of relative sign floating around, and it's important that we have a minus here. So let me now tell you about the minus. And the minus comes from the fact that these two curves, the 1, 1 and 2, 1, they are actually parts of ends of the same moduli space. So there is the moduli space of C1, 1 and 3 negative punctures at the A1, 2, A3, 2, A2, 3. Same here, now A2, 1 I should have said. So, but now these two disks here, they are related by cyclic permutation. And everything we do is invariant under this cyclic permutation. So in particular, they have the same sign. And since these are boundaries of a one-dimensional moduli space, these two guys must have opposite signs. So that tells us that, that tells us that there is a relative minus sign between these two terms and those two and those two. And then we need to check that we can actually cancel things. So now we're almost in business. Maybe I go back. So what we need to check is this A power. So we have this one curve, and we need to cancel that one by that one. So basically, the A power sitting in this disk divided by that one has to be related to other A powers. And the same type of argument shows that that's indeed the case. So I need to look a little bit. So here we see that, so A powers are multiplicative, and these are again boundaries of moduli space. So it says that this one times the A power of this B21 disk is equal to that one times the A power in B13 disk. And we go on like that, and we look at it. And you see that you can now solve for this, for example, B13 or B32 in two ways. And when you do that, you find that exactly the needed scaling is there so that we can actually cancel these equations. So in other words, if I go in the right direction, this thing is actually true. So we multiply by suitable A powers, sum it all up, and the sum, and choose suitable gray curves, and the sum is something that actually annihilates the partition function. So that's what we do. Okay, so we know that these operators kill partition function. So then we would like to understand that this is actually determines something uniquely. And here, I should also say this kind of A powers are crucial. So when you look at these operator equations and trace the A powers, there were 3 equations. They actually give you 6 equations. And the first equation, I should wrap up. So the first equation, I'm writing it now as 2 equations. It's some relating partitions on the, so I take the first step, I take empty partition on 2 of the legs and some other partition on the third one, and I get relations by sort of relating. I get the system for partitions that looks like this, and the other one has 1 box in the next row. So this system of equation relates partitions to the next one, and the key point is that when you look at it, it has a determinant that is non-vanishing. So therefore, I can sort of recursively solve for all the lambda. So basically what I'm doing is I take all the lambda, I want all partitions, and I start with all partitions that go as just 1 row. And I do it by taking 1 row and 1 box. So the system of all such I first solve. And then I go down, I have all the first row, and then first row and some, and 1 in the third row, and so on. And then the equations actually just go on like that. So now I fix all the lambda partitions, and so I now start inducting on, say, another lambda 3. I induct on lambda 1, I have to go through all of them, and finally on lambda 3, and then I get uniqueness. So because of this determinant as is. And it's a sort of interesting exercise to see that the given formula satisfies this recursion. It's not completely trivial, but it's a manipulation with short functions. So I'm not going to say much about this. So I think I'll stop here and take questions.
Is there any question?
Thank you for a lovely talk. Quick question about, is there a refinement version on, and can you comment on skein perspective on?
Sure, yeah. So I mean, so for everybody else, there is something known as the refined topological vertex, which is a similar count, but it goes by two variables. So it's Q and T, and it has some origin in all this string theory. And I have some hope that these, so you see, we had, so our 3 equations somehow became 6 equations. And that's, I think by putting sometimes Q and sometimes T, you can find this thing. And the problem is that I don't know exactly what it means. So for these operators, it means you have to split the action depending on representation. I didn't manage to write it in a reasonable way here. For the, if you restrict to symmetric representations, oops, then there is some kind of recursion for the interesting extra brain, and that one I know what it means in terms of, it's some capping operator you have to change. So not yet, but hopefully at some point. And there is a wealth of things that should maybe come out of there relating to whatever, everything you already related to categorification and so on and so forth. But so not yet, but hopefully. And it's not gonna, in some sense it means that it is not really standard holomorphic curve theory, and it's not so easy to find, especially these things at infinity, how to make sense out of. It has to split up a little bit.
I had a question. So if you understand the vertex, could you also understand the gluing of vertices to treat, say, general toric?
Yes. So the gluing of vertices in this scenario works as follows. So you have this torus sitting somewhere, and in the spirit of SFT, you should now do some kind of SFT stretching. And that means that your holomorphic curves fall apart into something that from the outside limits to Rabe orbits, then from Rabe orbits into zero section. So what one, or yeah, we actually understand this picture, but the point is that these orbits down to zero section gives you an isomorphism between some kind of power sums of orbits and these W lambdas. And when you now do the gluing in terms of Rabe orbits, you can sort of throw away the Lagrangian, and you, so you get it, and there is a natural picture for that. Yeah. And I should also say that in general this mixed, I mean there was this talk from you. I saw you were there. This Gupa cover talk yesterday. So these Rabe orbits and going down to boundaries, some sort of, in some sense, map between what they call these F strings and V strings or something. So the orbits are F, and then the ones on the boundary are V. So sometimes it mediates this change of variable. Okay.
Is there more question? No more question. We thank the speaker again.
Thank you.